Swayam Prabha. Digital India. Educated India.
Welcome to lecture 5 of module 7. In this module 7 we have been discussing on heat exchanger, and the last 4 lectures we have discussed various types of heat exchangers, their configurations, their structure and their various parts, and also we have discussed that effectiveness NTU method of analysis of the heat exchanger. And now today's lecture and the next lecture, that means in a couple of lectures we will be discussing on design calculations for the heat exchangers, and for that reason we will be taking up two most important heat exchanger types. These are double pipe heat exchanger and cell and tube heat exchanger. In today we are going to discuss on design calculations for double pipe heat exchanger. So, in today's lecture we are going to discuss specifically on double pipe heat exchanger and how to design, how to do the calculations for designing this heat exchanger. But before we go for these design calculations, we would like to discuss some important issues and some important parameters which may be or sometimes are required for the design calculations. The first thing we should discuss on the overall heat transfer coefficient. So, important parameters or relations. Okay. Now, in this first we will see that overall heat transfer coefficient already we have discussed. So, basically what is happening, overall heat transfer coefficient means it is the heat transfer coefficient based on the total resistances that may lie in the heat exchanger. We have discussed partly on that. And if we take just for an example, if we take a case of the double pipe heat exchanger. So, this is the double pipe, this is the concentric pipe, this is the center line, and this is another pipe over here. So, possibly this is the thickness of the inner pipe, and this is the center line, and this is the outer pipe. So, what are the resistances that we know? That there are 3 resistances can exist. One is the film inside here, and there is the resistance for this wall thickness, and another is the film outside the inner pipe. So, these are the 3 resistances that may exist, resistances for heat transfer from one fluid to the other fluid. There are 2 fluids, one fluid is passing through the, in case of double pipe heat exchanger, one fluid is passing through the inner tube, and another fluid is passing through the say annulus, and in most of the situation it happens to be a counter flow situation. Okay. And in that case, we know that there are 3, if there are 3 resistances from the resistance series model we have discussed long back, that driving force is, or the current is driving force by the total resistances. So, current is equal to, in this case is the Q dot, and that will be the driving force is the delta T between the 2 fluid stream, and divided by the summation of resistances, that is the R I, total resistances. And there are 3 resistances possible, as we know. This is the inlet the resistances due to the inside film of the inner tube, outside film of the inner tube, and the resistances due to the thickness of the tube, and that is in that case we can write like that way. And these equations also can be written as, now AI is the surface area of the inner tube into UI. Inner UI is the heat transfer coefficient based on the inner tube area into, and this is Ti minus To Ti is the inner tube temperature, say Ti, and outer tube temperature is the annular temperature is To. So, that is the temperature difference is the driving force, and that also can be written as AO UO into Ti minus To. So, this is basically this is a delta T, and here that means 1 by AI UI or 1 by AO UO. These are the total resistance, and that is equal to summation of Ri, and these total resistances is based on the that Ui and Uo are the overall heat transfer coefficients. These are based on internal area inside area of the inner pipe or based on the outside area of the inner pipe. So, based on that, if we just do this, then what we will get is that Ui already we have discussed, this will be equal to 1 by Hi plus AI ln Ro by Ri divided by twice by K into L. K is the thermal conductivity of the wall material, plus we have AI by AO into 1 by HO. This is what? So, this is in terms of, or UO can be written as in the similar fashion, this by AO by AI into 1 by HI plus AO ln Ro by Ri divided by twice by KL plus 1 by HO. So, these two cases, this is resistance of the inner film, this is the resistance of the tube length, and this is the resistance of the outer film. Here the resistance of the inner film, this is the resistance of the tube thickness, and this is the resistance of the outer film. So, the only thing is that they are based on the different areas that are being calculated, and we know that AI is equal to twice pi Ri into L and AO is equal to twice pi Ro into L, okay, for the tubes. Fine. So, in that case we can finally write that Ui is equal to 1 by Hi plus Ri by Kw into ln Ro by Ri plus Ri by Ro into 1 by HO, fine. And then similarly U also can be written as 1 by Ro by Ri into 1 by Hi plus Ro by Kw, sorry, Ro by K. Kw is not necessary, Kw means K or Kw, what is that? That is thermal conductivity of the wall material for the tubes, by K into ln Ro by Ri, okay, and plus 1 by HO. We have seen in case of conduction that ln Ro by Ri by twice by KL, this becomes the resistance in case of cylindrical body. Okay. Now, if we so this is becoming the final expression in terms of radius. Now, here one thing we have not taken into consideration, which is called scale factor or the dot factor, whatever it is, that happens due to the deposition of scales on the surface of the tube. So, as we have seen in the first case, that there is a tube and there is another possibility, the addition of resistance due to formation of the scale here on the surface and on this surface. So, there is a possibility of formation of the scales, and which is nothing but is called the dot also. So, if we have to take into consideration of this dot factors of the scales, then we can write that the resistance says due to scales, we can write as 1 by AI HSI and 1 by AOH SO. What are these? HSI is the inside surface of inner pipe, the scale for a heat transfer coefficient HSI. So, it is expressed in terms of equivalent to an heat transfer coefficient, because it is, though the scale is a solid material. So, the resistance could be written in terms of a the thickness in terms of a solid material, but it is difficult to measure the thickness of the scales that is being formed is a very fine amount. So, therefore, many a times it is expressed in terms of in terms of equivalent to a heat transfer coefficient like this. So, HSI is that is the heat transfer coefficient in the inside, as I indicates that inside surface of inner pipe for the scales formed. Similarly, HSO is the heat transfer coefficient in outside surface of inner pipe due to scale formation. Okay. So, this is the coefficient, these are the coefficients for this. So, these things are to be these that 1 by HI AI into HSI and 1 by AO into HSO. These are the two additional resistances which can come along with the 3 resistances we have seen. In that case, we will be having total 5 resistances in a double pipe heat exchanger, or similar kind of behavior can be there in case of cell anti heat exchanger also. In place of the annulus part, there will be a cell basically, otherwise there will be the resistances will be again this 5 resistances would be involved. So, therefore, considering the scale formation, so expressions can be, so Ui dash, that is the change to 1, which should be 1 by as we have seen 1 by Hi plus 1 by Hsi is the based on inside heat area plus Ai ln Ro by Ri, that is already we have seen, and then 2 pi k L plus Ai by A naught outside area 1 by HSO, this for scale, plus Ai by A naught into 1 by HO, fine. And then Uo dash would be 1 by Ro by Hi into 1 by Hi in terms of, this is in terms of radius now. This is similarly, if I write this is in terms of radius. So, if I write in terms of fine, this will be plus Ro by Ri 1 by Hsi, this will be Ro by Ri in terms of radius, Ro by Ri into 1 by Hi plus Ro by Ri into 1 by Hsi. Here I have written in terms of area. Now, this part is I am written in terms of radius. This just requires the 2 pi k L, you have to multiply, that is all, 2 pi L, you have to multiply, you will be getting in terms of the area. So, this plus you will be getting Ro by k ln Ro by Ri plus 1 by HSO plus 1 by HO. So, this part this part again I am repeating that this part is written in terms of radius and this part is written in terms of the area. So, this area part can be written again in terms of the radius just by multiplying with 2 pi L in up and down. If I multiply, multiply with 2 pi L, then we will get that in terms of this. Okay. Now, some typical values of these fouling factors. So, this 1 by Hs, rather fouling factors which is nothing but 1 by Hs, it can be Hsi for inside case and HSO for the outside case, and this fouling factor is it is actually dependent upon the type of fluid that is being used, and its unit is meter square per Kelvin per watt. So, under that situation, for different types of fluids, if we see that for distilled water, then liquid gasoline, then fuel oil, crude oil, that 1 by Hs is nearly equal to 0.000086, that is meter square per Kelvin per watt. And for cases like sea water, okay, then boiler feed water, okay. Similarly, say diesel exhaust gas, etc. They have 1 by Hs is nearly equal to 0.000172 meter square plus Kelvin per watt. So, these are some representative values for different types of fluids. It can be liquid or gaseous fluids, and how much is becoming their scaling factor. So, this is what is just to have an idea. The next part what I am going to discuss is this caloric temperature. Caloric temperature is a temperature that is calculated when there is a continuous change, and there is actually what happens is in a heat exchanger there is a continuous change of heat transfer, continuous change of temperature from one end of the heat exchanger to the another end of the heat exchanger. There is a continuous change, but if the change in temperature is very high, and if the density, if the viscosities of the fluids are also is a strong function of this temperature, under these two situations, that means what I am saying is that if the change in temperature in a heat exchanger along the length is high, that means greater than say 30 degree centigrade or so. If the change in temperature is high, or second case is that if viscosity of fluid is highly sensitive to temperature change, then under these two cases, when these two cases satisfy or any of the cases satisfy, then caloric temperature is used, and this is proposed and details are proposed and details are available in the book of D.Q. Kern on process heat transfer okay. Tata McGraw-Hill edition, Tata McGraw-Hill edition, and year 1997. Now, this is proposed by Kern, and details are available in the book of the Q. Kern. Okay, how to calculate this caloric temperature? Then, in that case, in otherwise, when these two things are not there, otherwise the average temperature of the fluid are being taken. So, caloric temperature is used to estimate the properties, rather I should say thermophysical properties okay, of fluids. Otherwise, that means when it is not needed, otherwise means when caloric temperature is not needed, as we have seen the cases okay, previously, the two conditions. Then when caloric temperature is not needed, then average bulk temperature between two ends okay, are or rather is used for for the estimation. If we see that whether it is a parallel flow or counter flow in either of the situations, if we just see the cases like this, just to have a little sense on that, this is T H 2 and here it is T H 1. So, hot temperature is T H 1, okay, and cold temperature is entering at T C 1 say, and cold temperature is going at T C 2. So, here it is entering at T C 1, it is, and this is T H 2 and here it is T C 2. So, what happens is that T H C is the caloric temperature for the hot fluid, and that is given as T H 2 plus, this is the caloric fraction rather, T H 1 minus T H 2, and T C C, that the caloric temperature for the cold fluid, is given as T C 1 plus F C into T C 2 minus T C 1. If you see that in both the cases, so T H 2 and T C 1 are the cold temperature, lower temperatures, and T H 1 and T C 2 are the higher temperatures for the hot and cold fluids. So, and F C is called caloric fraction, and that needs to be calculated. So, then we will get a THC and TCC, these are the caloric temperatures of the hot fluid and the cold fluid, and the details are available in the book of currents. Okay. Now, what will be some other points we are going to see that we will be discussing during the calculations. Now, some important points while doing the calculations for double pipe heat exchanger. So, double pipe heat exchanger design calculations. So, some important points that we have to see, what are these, that in this case what we have to estimate heat transfer coefficient, inside heat transfer coefficient based on outside area, this is inside heat transfer coefficient, inside film heat transfer coefficient, this is the inside film heat transfer coefficient based on outside area, and then overall heat transfer coefficient, okay, and then to estimate UD, that has to be done, that is the this is for say clean case, and this is for dirt case when there is a fouling factor. So, we know that 1 by UD is equal to 1 by UC plus RD, RD is the dirt factor. Already we have seen that kind of factor, and this is the clean overall heat transfer coefficient, this is the overall heat transfer coefficient, and UD is also overall heat transfer coefficient where which takes care of the dirt. So, that means the resistance, another additional resistance due to the formation of the scales. Okay. And then this is the first thing. Second point is placement of fluids, where to put which fluid. So, if we have in the double pipe heat exchanger there are two flow regions, one is the tube inner tube region, another is the annulus region. Where should we put which fluid? So, it depends upon that. We have to see this, check the pressure drop, delta P case, and if delta P allowed. So, we have to see that what is the allowed or allowable pressure drop for two streams. If we see that both the fluid streams are of similar pressure drop, the allowable range is of similar nature, then so if delta P allowed is similar for both fluids, then one should see that both the fluids are getting similar kind of delta P. So, that accordingly the flow distribution should be made to see that similar mass velocities and similar delta P are desired. So, in that case similar mass velocity and delta P are desired for tube side and annulus side fluids. Okay. So, this is one consideration, that how to place the fluids, and then we have to know the various process conditions. That includes thermophysical properties, flow rates, temperatures, etc. So, this has to be known, okay. And then order of calculations. If you say that in case of double pipe heat exchanger, order of calculation says that first we have to calculate the energy balance for the cold fluid, heat fluid and overall energy balance. Then we have to see this LMTD estimation, and in double pipe it is usually counter flow in double pipe, because we have already discussed at some point of time that counter flow situation usually gives better heat exchange, that's due to maintenance of the uniform delta P all through the heat exchanger, and that is particularly true when we have a double pipe heat exchanger. And then the third point is that there is another point, that caloric temperature, whether to find caloric temperature or not, whether we have to find out the caloric temperature or not, that to be decided based on, need to find out based on delta T and viscosity range, viscosity or nature, delta T and nature of fluid. That is very important. Then, so this is in general, and then after that comes the calculation for inner pipe, okay. And calculation for inner pipe, what we have to calculate the flow area, okay. Then we have to calculate mass velocity. This is equal to, say, tube side is equal to pi dt square dt flow I, dt I square by 4, and this will be equal to gt, and that it will be equal to W mass flow rate divided by AT, okay. And then caloric temperature calculation if needed, okay. Then comes Reynolds number calculation for tube side, it will be dt I into gt by mu t dv rho by mu, that we know that. And then calculations of hi from C dot A or other correlations. From correlations, okay. Then once we know that, then we can calculate HIO. So, these are the calculations for inner pipe. Then we have calculations for annulus, okay. In the annulus, what are their flow area again, that is a area, and that is to be calculated. This is pi by 4 into, say, di square, that means inner diameter of the bigger pipe minus that tube outer diameter whole square. Then comes that equivalent diameter, that is very important, this equivalent diameter is different for pressure drop calculation, and this is different for heat transfer calculations. So, this is equal to dE is to be calculated 4 into flow area by weight at perimeter, okay. And then estimation of mass velocity Ga, and that will be equal to W annulus by A annulus. Then calculation of caloric temperature if needed, and accordingly estimation of properties, thermophysical properties. Okay. This is similar for the previous case also. Here caloric temperature if needed, and accordingly estimation of thermophysical properties. Okay. And once we know that, then we have to go for Reynolds number, estimation of Reynolds number, okay, annular regions, it is dE into Ga by mu, and then estimation of HO from correlation, and then after we do that, then we have overall coefficient computation of overall coefficient. So, what is that is compute UC, and that is equal to HIO HO by HIO plus HO, and then compute UD, and that is equal to, that is from like this, 1 by UD is equal to 1 by UC plus RD, already we have discussed, this is a dart factor. Then compute A, the area of heat transfer from Q is equal to UA delta T Lm, log mean temperature difference, and then compute length of the heat exchanger, and then comes the calculation of pressure drop. So, that happens to be for cell, sorry, not for cell, tube side fluid. There are two type of pressure drops, delta P total is equal to delta P T plus delta P R. This delta P T is for this is for frictional losses, and this is for return loss. This return loss is due to bending of pipe and return of liquid by changing the direction of flow. So, that means if we have a tube and tube bend, that means the tube fluid is going back. So, it is a return mode. Okay. Therefore, that because of this bend, the change in its direction, there will be a loss, and that loss is called return loss. Okay. And so, these values has to be calculated, and for cell side similarly we have, there are two First you have to calculate the shell side, or here it is annular side. So, annular side, again that D estimate nu D, that means here we have to take that because during the pressure drop the frictional loss can happen for the fluid touching the inner surface of the outer pipe, and therefore, that frictional losses has to be taken care of from that, and therefore, that D will be a different. So, effective diffusivity that effective diameter will be different, or equivalent diameter will be different, and then delta P total in this case also will be delta P T plus, here also we can say that delta P loss. So, here this is again the frictional loss, and if I say R, again this is frictional loss. This is also, it can be it is usually that entrance and exit losses. The reason is, in case of double pipe heat exchanger, that material comes from one side and then goes. So, that will be an entrance and exit losses. Okay. Now, we will take up a problem to discuss this problem. Say benzene, the problem statement is like this, that benzene is cooled from 70 degree centigrade to 50 degree centigrade in a counter current double pipe heat exchanger. Okay. Fine. The flow rate of benzene is 800 kg per hour. Okay. Tubes are made of carbon steel. Okay. And inner tube ID is equal to 21 millimeter, OD is equal to, ID means inner diameter, OD is equal to outer diameter 25.4 millimeter. Outer tube ID is equal to, means inner diameter is equal to 40 millimeter and OD is equal to 48 millimeter. Okay. Inner tube specification is this, and outer tube specification is this. Okay. Now, coolant water, okay, enters through the inner tube at 30 degree centigrade and leaves the inner tube at 40 degree centigrade. So, do the necessary calculations to find the length of the heat exchanger and the corresponding pressure losses. Okay. So, what happens is that this problem says that we have a double pipe heat exchanger. In the annular side, the benzene is there, and in the through the inner pipe we have a water. The benzene is at higher temperature, it is at from 70 degree centigrade to 50 degree centigrade is to be cooled down, and that is being done by a coolant, that is the water again, and it is entering at a temperature of say 30 degrees centigrade, and it is leaving at a temperature of 40 degrees centigrade, and the flow is counter current in nature. So, what we have to find out? We have to find out that heat exchanger area, and from that area we have to find out the length of the heat exchanger. At the same time, we have to find out that pressure drops whatever is happening in both sides of the double pipe heat exchanger. Now, to start with the solution, just a rough sketch of the temperature profiles. If you see this length, and this is station 1 and this is the station 2 double pipe heat exchanger, and it is a counter current flow. So, here it is 50 degree centigrade, and then it is 70 degree centigrade, and then here it is 30 degree centigrade, and there it is 40 degree centigrade. So, this is delta T 1, it is this is 30 degree centigrade, and here it is 20 degree centigrade. Fine. Now, average temperature of hot fluid, that means of benzene, is equal to 60 degree centigrade, and average temperature of water is equal to 35 degree centigrade. And if you see that temperature difference maximum is for benzene, and that is equal to 20 degree centigrade. Both the fluids are not highly sensitive, fluids viscosity. Are not highly sensitive to what is that called temperature. So, calculation of caloric temperature is not necessary. That is one point. Second point is that LMTD is equal to delta T 1 minus delta T 2 by ln delta T 1 by delta T 2, and that is equal to, we know, say 30 minus 20 by ln 30 by 20, and that is equal to 24.66 degree centigrade. In addition to that, if I just do the energy balance, if we try to see the energy balance, it gives that Q dot is equal to W hot fluid CPH into T H. So, before we go for the energy balance, okay, this is equal to TH1 minus TH2, and that will be equal to WC into CPC into TC2 minus TC1. Now, we have to find out all these physical properties, thermophysical properties. So, for benzene at 60 degree centigrade, which is the average temperature, we should say that Cp is equal to 1880 joule per kg per degree centigrade, then mu equals to 0.36 Cp, and that is equal to 3.6 into 10 to the power minus 4 kg per meter per second. Mu is this, rho equals to 860 kg per meter cube, and K is equal to thermal conductivity equal to 0.153 watt per meter per Kelvin, and for water at 30 degree centigrade, we have mu is equal to 0.8 Cp, and that is equal to 8 into 10 to the power minus 4 kg per meter per second. K is equal to 0.623, and Cp is equal to 4180 joule per kg per degree centigrade. And then from the energy balance, we can say that Q dot is equal to 800 into 1800 into 70 minus 50 and that is equal to 288,000,000 joule per hour. And then WC we can find out from here. WC is becoming 689 kg per hour, and that is equal to basically 288,000,000 divided by 4180 into 10. So that is, we get the W. Then comes inner pipe calculation. Inner pipe calculation says that flow area is 3.64 into 10 to the power minus 4 meter square. It is equal to pi into dTi square by 4. Then flow rate equal to 689 kg per hour. Mass velocity, that is GT, is equal to W by AT, and that is equal to 689 by AT is known. So this is becoming 552.78 kg per meter square per second. You mind it, it was converted into seconds, so divided by 3600. Fine. And then Reynolds number for tube side fluid is equal to dTi GT by mu T, and that happens to be 14510. If we do the calculations properly, we will get this, and Prandtl number will be getting as mu Cp by K, and that is equal to 5.37. And then what we will do is, in this case we will use that Cedar-Tate relation, that says Nusselt number based on diameter is equal to 0.027, Reynolds diameter to the power 0.8 into Prandtl to the power 0.33 into mu by mu W to the power 0.14, and this is mu by mu W is equal to 1.0, there is no correction. Okay. And then we have Nusselt number is based on diameter will be equal to 29 and Nusselt number is equal to Hi into dTi by K. From here we can find out that Hi is equal to 2978 watt per meter square per Kelvin or per degree centigrade, whatever it is. And then HIO will be equal to Hi into Id by Od, and that is becoming 2462 watt per meter square per Kelvin. Okay. And then comes that annulus calculation. Annulus calculation says that flow area is equal to pi by 4 into, as I have said, minus dTo square, and that is equal to 7.5 into 10 to the power minus 4 meter square, and then equivalent diameter is equal to flow area by this, so it is becoming 0.0376 meter. And then mass velocity is coming as 296 kg per meter square per second. So it was initially per hour, now it is converted into second, and then we get a Reynolds number is equal to dGA by mu, and that happens to be 309156, and Prandtl is equal to mu Cp by K, and that is equal to 4.424. Again applying Cedar-Tate equation for turbulent flow, what we get is HO we get as 4427 watt per meter square per Kelvin. This is what we get, and then after that, once we get HO, and then we have to find out overall heat transfer coefficient calculation. Here we will get that 1 by UO is equal to RO by RI into 1 by HI plus 1 by HO plus RO by K ln RO by RI, and that is equal to 1 by HIO plus 1 by HO plus Rho by K ln Rho by Ri. Then if we put these values over here, we will be getting 6.643 into 10 to the power minus 4, and from there UO is equal to 1505 watt per meter square per Kelvin. Here one thing I should say that wall resistance, if we do the calculations, inside calculations, is about 5.1% of the total film resistances. Total film resistances. So that is much less. The wall resistance is nothing but this one, and these are the total film resistances. This is nothing but the total film resistances. Okay. Now I have got UO now. Now what you have to find out is that RD will take as for two different fluids, will take RD as 0.000172 for one side fluid plus 0.000088 for the 86 for the other side fluid 86. So this is total becoming actually 0.000258 meter square per Kelvin per watt. So one side fluid is the water side, and one is water, another is for benzene. Okay. So we will take something like that, and then what we will get is UD will get from the relationship of this, and UD we can find out 1084 watt per meter square per Kelvin. Now once I know UD, then we can find out area based on the outside diameter will be 28800 by UA delta T. So 3600 is that for hour, 1084 into delta T LM is 224.66 meter square, and that is equal to 0.3 meter square. So length of heat exchanger is basically 0.3 by pi into 0.0254 outside diameter of the tube, and that happens to be 3.76 meter. Now to go for the pressure drop calculations. So pressure drop calculation, for tube side fluid, we will make use of this relationship that F is equal to 0.0014 plus 0.125 by RE to the power 0.32. This relationship is given by Drew, Koo and McAdams for relatively smooth tubes. So if we use this relationship for pressure drop calculations, then and delta P is nothing but it's a Darcy's friction factor into G tube side whole square into L by 2G then rho T into dt naught. So here this GT we know, FD is Darcy's friction factor, we can calculate from here. L is the length of this, and G is the due to gravity, rho T we know, and dt also we know. Then if we put all the values 0.0289, that you can calculate from here. Okay, factor friction factor. So FD, Darcy's friction factor, is the 4 into F, Fanning's friction factor. So if we put these values here into 552.78 square. So if I do in the next page, so delta P here is 0.0289 into 552.78 square into 3.78 length of the heat exchanger by 2 into 9.8 into 1000 in the density of water approximately into 0.0254. Okay, so this becoming actually 66.7 kg per meter square, and this is nearly equal to 0.0667 meter of water. So this is the pressure drop, and there is no return pressure drop for the tubes, assuming no tube bend, because length of tube is 3.76 meter. So, if there is a tube bend, then we have to calculate this. So, we are not calculating that part, and then for cell side or say annular side, for annular side again. So, delta P again similarly F D G A square, this for annular side G A square into L by again 2 G rho A annulus into D E dash. This is the equivalent diameter, and that equivalent diameter has to be calculated based on the total these things. So, equivalent diameter is 4 into flow area 7.5 into 10 to the power minus 4 by weighted perimeter is changing here, pi into DTO outside diameter plus DI inside diameter of the outer pipe. So, this is becoming now 4 into 7.5 into 10 to the power minus 4. This is very important actually, pi into 0.0254 plus 0.04. So, this gives us 0.0145 meter. So, this then becomes F D is equal to after calculation F D is becoming F D is from that relationship. So, this is becoming now roughly 0.40.44 kg per meter square. So, this is nearly equal to 0.047 meter of benzene. So, if I express in terms of benzenes, okay. But there is another, the exit entrance and exit losses. So, this is as we said that it is V A square by 2 G into rho A. So, nearly equal to G A square by twice rho A into G, and this is equal to 5.19 kg per meter square. So, total loss equals to 45 point, add of these two, 40 plus 5, 45.63 kg per meter square, which is equivalent to 0.053 meter of benzene. So, this is the pressure head. Okay. So, the pressure drop we have in the annular side we have calculated based on this frictional loss. This is the frictional loss, and this is the entry or entrance or exit losses. And in case of tube side, we have calculated only due to the frictional losses. So, this way we can find out the pressure drops and see that whether this pressure drops is lying in our allowable limit or not. So, this is all about today, and in the next lecture we are going to discuss on cell and tube heat exchanger calculations. Thank you very much.